Today we will be discussing resistive forces. This presentation is being done by Elise, Ben, and Sophie. To introduce our topic today, we will start with the problem being addressed. We proposed how mass will affect velocity and resistive force exerted on an object. We proposed the question, how does increasing the mass of paper plates affect its velocity and the resistive force from the air? Our goal was to examine the relationship between the velocity of paper plates falling through the air and the resistive force from the air. Our results concluded that as we increased the mass of the paper plates, the velocity and the drag force acting on the plates also increased. We will now discuss the models at study. The main ideas that we are studying are kinematics, which is how velocity is affected, force, how drag force is affected, and Newton's second law, which is F net equals ma. Here, you can see that heavier weight equates to a larger magnitude of drag force, as you can see in the free body diagram. The more plates bundled together, the higher the magnitude of the drag force. Heavier weight also equates to a higher velocity. The more plates that are bundled together, the higher the velocity, meaning the faster the plates fall to the ground.
For our experimental design, we taped 2 meter sticks to the wall to ensure an aligned coordinate system. We then dropped 1, 2, and 3 plates respectively from the top of the second meter stick and recorded multiple trials of the drops with an iPhone. We imported the data from each drop to Tracker and collected data from each drop, analyzing the velocity where it begins to flatten and approach terminal velocity. Then using the equation for the force of drag, we can determine how increasing the mass affects the resistive force acting on the plate. Some of our potential errors were that Tracker can only track every frame instead of the instantaneous movement. The paper plate does not fall uniformly because it can change orientation as it falls, which then would affect the drag force on it differently. The paper plate did not fall exactly straight down. It moved around as it fell, which impacts how Tracker reads the plate's position and calculates its velocity. To minimize these errors, we did several trials for each mass and used the best video for each trial where the plate fell relatively straight with minimal changes in its orientation. Trials were done indoors to minimize any additional wind affecting the plate as it dropped.
Okay, for the qualitative conclusions, you can look at the velocity versus time graph for each of our trials, and you can see that as we increase the mass for each trial, that the terminal velocity was also higher. And with higher terminal velocity, you get a higher drag force. And you can see this by looking at the equation for drag force. If you set the net force equal to the weight force minus the drag force, and you know that at terminal velocity acceleration is 0, then the force of drag is equal to the weight force, and using the equation for drag force, you get that the weight force is equal to that equation, and solving for velocity, you get that. And as you can see, as you increase mass in the numerator, velocity, the whole thing's going to increase, and so is velocity. And with the velocity increase, you will get a higher drag force. And the quantitative conclusions, we found our Tracker data looking at the average terminal velocity around when the curve began to flatten out, and we used the drag force equation. We found the area of the plate to be 0.051 meters squared, so we set up for the A value, and we also assumed that the density of the air was 1.225 kilograms per meter cubed, and that C, the coefficient of drag for the plate, was 1.28. So we got the values, and as you can see, for each mass increase, the drag force also increased, and we can see that the drag force is pretty close to the gravitational force at terminal velocity, which it should be. There's a little bit of error there. And also the constant of proportionality for the drag force, which we found for the force of drag over the mass, had an average of 9.828. So to explain the error for the difference between the drag force and the gravitational force, we can look at the standard deviation for each of our average terminal velocity values found in Tracker, and Tracker gave us the standard deviation for each velocity value. And so that error could potentially explain why the drag force is not exactly equal to the weight force.